Good morning. In today's class, we will discuss about burden distribution and followed by various chemical reactions which takes place at different parts of the blast furnace. The raw material which are required for the production of hot metal to the blast furnace are basically prepared, and it is stored in the stockyards, and from the stockyards to the conveyor belts to the using raw material handling systems like stock reclaimers. We basically send this raw material from the stockyard to the respective departments through the conveyor belts, where these raw materials are stored in the bunkers, or you can also call as silos. Each raw material is stored in different bunkers separately, and a common conveyor belt will be arranged below these silos. And a weighed amount of these raw material are collected on the conveyor belts, and this will be this conveyor belt will move, and it will allow to charge the raw material into the bucket where your skip hoisting system will be there, and this bucket will move up, and the raw material will be charged into the blast furnace. So previously, in the good olden days, starting the beginning of the blast furnace top is open. It's an open top furnace. So during the preparation of hot metal to the open top blast furnace, the blast furnace iron makers has observed that a huge amount of heat in the form of waste gases are emitting out of the blast furnace, and it is joining into the ambient atmosphere, and there it is getting combusted. So they thought that if you can collect that waste heat going out from the top of the blast furnace, so that that heat can be utilized within the steel plant itself. Okay. So with this idea, they come up with a closed top system where you have, you can see this kind of uptakes are arranged, and these uptakes are connected to a downcomer, and of course the downcomer is again connected to the gas cleaning system. So during charging of the raw material into the blast furnace, they observed that certain amount of waste gas are getting leaked out from the blast furnace. So to overcome that, they come up with a bell type of charging system. A double bell charging system they have arranged as that during the charging of raw material, the waste gases will not get escape out from the blast furnace. So here in this picture, you can see that you have a double bell charging system is arranged. This is called a small bell and this is called a big bell. And you can see a skip hoisting system is there here, where you can see this is the bucket, okay, where the raw material has collected into it, coming from the various silos, collected on a common conveyor belt and fallen into this bucket. And that bucket will be traveling up, and then it will be discharged the raw material into the hooper. Here you can observe that there is a hooper for both the bells. For small bell, there is a hooper here at the top, and for big bell, this is the hooper. So the working of this type of charging system, if you see that these two bells are lowered down one after other. Means when one is in the closed condition, the other one will be in the open condition. So you can close and you can open these bells by just lowering down and rising up. There is a rod kind of system is there here, where you can lower down this so that the bell will be open condition, and if you rise up, bells will be in the closed condition. This open and closing system of the bells will happen when, suppose, when the small bell hooper is filling down. When small bell hooper is filling, then in that case, the small bell will be in the closed condition and big bell will be in the open condition. When the small bell hooper is filled, then certainly this small bell will be lowered down so that the raw material, whatever it is collected in the hooper, that will small bell hooper, that will fall down into the big bell hooper. So when it is falling into the big bell hooper, at that case, the big bell will be in the closed condition. So in this step 2, you can see that small bell is in the open condition and big bell is in the closed condition. Now, step 3, if you see, once the big bell hooper is filled, then to discharge this raw material into the blast furnace, we should lower down the big bell so that this raw material will fall into the blast furnace. In that case, when the big bell is in the lowered down condition, in that case, the small bell will be in the closed condition. So in this way, you cannot allow any gases to pass through like this. Rather, it will actually go through the takes. So when one bell will be in the closed condition, the other bell will be in the open condition, and vice versa. In that way, the raw material is basically charged into the blast furnace. And the distribution of these raw material is basically altered by armor plates. Here you can see there are armor plates are arranged at the two sides of the blast furnace. So you can push these armor plates front and back so that this movement of these armor plates front and back will allow the raw material to fall from the center to the periphery. So whenever you want to allow the or distribute the raw material to allow to pass and fall in the center of the blast furnace, then you push the raw material, sorry, push the armor plate little inside so that the raw material will fall onto the armor plate and it will be settled down at the center. If you want to allow this raw material to fall at the periphery, then you pull back this armor plate so that the raw material will fall at the periphery. So this is how we can um, allow the burden or allow the raw material to fall into the blast furnace at different locations. But during the meantime, the blast furnace operators have encountered some problems with the bell type of charging system. One is the erosion of these bells because of the movement of the burden or because of the impact of the burden on the bells. There is erosion of the bells usually used to encounter, because of which gases used to pass through from the gaps. And because of this erosion problem, there is replacement of these bells used to be happen 2 to 3 times during the campaigning life. For a normal blast furnace, the campaigning life will be around 10 to 15 years. So during this time, because of the erosion of these bells, you can see this is one bell. This is the bell. This is the size of the bell. This is how the bell looks like actually. Because of the impact of the burden, because of the erosion of these bells, the gases used to be leaked. And also nowadays, all blast furnaces are operated with a high top pressure, because of which also the bells used to get eroded, and that leads to the gas leakage. So for this reason, now the bell type of charging system, the double bell charging system, is completely replaced with the bell-less top charging system, where we have replaced bell. In place of bells, we have a rotating chute. You can see this is the rotating chute we have. Okay. And now you here also you can see in this particular picture you have a bunkers are there, storage bunkers, and you have regulating wall is there, where when one bunker is in the discharging mode, the other bunker will be in the charging mode, and here there is a wall will be there which is closed, okay, when the other bunker is in the charging condition, for discharging condition. So when this bunker is empty, now here the wall will be closed. Now here the wall will be opened. Now the raw material will fall from this particular bunker, so that there won't be continuous distribution of the raw material will takes place into the blast furnace. And here you have a rotating chute is there, and this rotating chute rotates in the circular manner, and also there is a provision for the inclination also, inclination of this rotating tube. So with having this kind of a arrangement, you have a provision for the uniform distribution of the burden inside the blast furnace from the periphery towards the center. So whenever you want to charge the raw material at the center part and also just little bit tilt it, the rotating chute, so that the raw material can be charged at a particular location. So wherever you want to charge the raw material at that particular location, you can incline in such a way so that the raw material will fall at a particular location. So the raw material actually charged into the blast furnace in a concentric circles. You have around 10 to 12 circles will be there in the blast furnace, and depends upon the usually we allow the coke and all to fall at the peripheral zone. First few rings from the peripheral zone will be of mostly of coke based burden will be there, and when you are moving, and at the center also again you have coke will be there, and the rest of the rings you'll be filled with the iron bearing material majorly along with the flux and coke. Okay. So this is how the distribution of the burden will basically takes place inside the blast furnace. We have to allow this burden to fall into the blast furnace or distribute the blast in such a way that this bed of solids should have very good permeability. Okay. And also, whatever the burden we are charging into the blast furnace as a part of a raw material for hot metal production, make sure that these burdens should have a good quality, and it should have good properties so that it can withstand its original size and shape, and not to generate too much of fines inside the blast furnace. Generation of any high quantity of fines inside the blast furnace is not good for proper running condition of the blast furnace. It will hamper the it will you can lose the permeability of the bed, because of which wind the aerodynamics of the blast furnace will get hampered. Okay, so to make sure that the bed should have good permeability, and the blast furnace can run efficiently and effectively without having any hanging or those kind of situations. So once you charge the raw material inside the blast furnace, then as we already discussed the blowing in process also, how to start the blast furnace. Okay, we have discussed about how to prepare the raw material and what are the testings we have to do for the raw material before we charge into the blast furnace. So once the raw material is prepared, once you are, and we also discussed about how to start the blast furnace. Okay, so once you have started the newly lined blast furnace or a shutdown blast furnace, then we have to create the burden cycle, starting cycles. Okay, and once we made the starting cycles, then you have to allow these raw material to undergo smelting process in that blast furnace, and various reactions which takes place at the different parts of the blast furnace, which leads to the production of liquid products, that is hot metal as well as the slag. So we'll see what are the various reactions which occurs at different parts of the blast furnace. The kind of reactions which takes place is purely depends upon in what form the, the reactants are at that particular location. Because blast furnace is a complex reactor where the at certain location of this furnace, the raw material will be in the solid form. At certain locations, it will be in the semi-solid form. At certain locations, it will be in the liquid form. At certain locations, there is a possibility that there will be interaction between the gas and the solids. At certain locations, there will be possibility that interaction of gas and the metal may takes place, and gas slag may takes place. And at certain locations, especially in the lower part of the blast furnace, there is a possibility that slag metal reactions may take place inside the blast furnace. Okay, so it is all purely depends upon in what way the interaction between the reactants is purely depends upon what is the temperature which is prevailing at that particular location, and in what situation the material is in. Okay, so it depends upon that we can categorize the the interaction between the reactants in like gas solid, gas metal, gas slag metal, and also the solid interactions also may take place at the blast furnace. Okay. So as we already discussed, there are different parts of the blast furnace. Starting from the top, you have a stack part. Okay. You have an upper stack, middle stack, and the lower stack, and you have then followed by belly region. Then you have a Bosch region. You have a pure region. Then you have a region of the blast furnace. So at all these different parts of the blast furnace, the burden will be in the different condition. So depends upon that condition of the burden as per the temperature which is prevailing there. The interaction between the reactants will be varying. Okay. So in the stack part of the blast furnace, if you see the entire burden, the raw material, whatever we are charging, the iron bearing material, the fluxes, the fuel. So these all are in the solid state. As the stack part of the blast furnace, the entire burden will be in the solid state. So certainly you can expect the interaction between the reactants will be gas solid reactions. Okay. So at the bottom part of the blast furnace, in front of the tuyeres, combustion of the coke takes place, and that leads to formation of carbon dioxide gas. But the carbon dioxide is not stable at that particular high temperature, so it will readily react with again carbon and forms carbon monoxide gas. So this carbon monoxide gas is formed at the tuyere part of the blast furnace in front of the tuyeres. It will travel up and it will interact with the metal material at the stack part of the blast furnace. So there will be always a gas solid interaction. Reducing gas, that is CO, will interact with the solid burden, and there will be gas solid interactions basically takes place at the top of the stack part of the blast furnace. So it is basically a counter current process. Okay, from the top, burden is continuously moving, and from the bottom, you are sending the reducing gases. So these two come in contact with each other in the stack part of the blast furnace, and there will be interaction between the gas and the solid, leads to the solid state reduction reaction basically takes place. The velocity of the descending raw material is much lower than that of the ascending hot gases, and as these solid descends, so the solid gradually get heated up because we are charging this raw material into the blast furnace at room temperature. Okay, so at the top of the furnace, if you see the off gas temperature will be of around 150 to 200 degrees centigrade. So the upper part of the stack, basically the only thing what happens is that the moisture content which is present inside the iron bearing material will be basically removed. Okay, in the topmost part of the blast furnace. So as the burden is moving down around 4 to 6 meters from the top of the blast furnace at this region, as the temperature of the iron bearing material will keep on increasing from the room temperature to around approximately 800 degrees centigrade. Okay. Then the reduction of the iron bearing material by CO basically starts, and there will be a heat transfer basically takes place between the gas and the solid, because the gas is carrying a good amount of heat, reducing gas, and this heat is basically transferred to the iron bearing material, and followed by there will be chemical reactions which takes place, solid state chemical reactions which takes place inside the blast furnace. So you can see reduction of iron bearing material will basically take place in this way. Initially we start with the hematite ore, and the hematite reacts with CO and forms magnetite, and then magnetite again reacts with the CO, will form oosterite, and oosterite reacts again CO or C, and it forms Fe. Okay. So this is how the solid state reduction reactions basically takes place in the stack part of the blast furnace. And this will start taking place. In fact, this reduction takes place even at very low temperatures itself. But the kinetics of this reactions will be faster at around temperature more than 500 degrees centigrade. And once the burden moves to the lower part of the stack, once it reaches to around 900,000 degrees centigrade, by that time most of the iron bearing material will get reduced to FeO or Fe form. Okay. Apart from this iron bearing material, at a temperature of around 900 degrees centigrade, there will be a dissociation of carbonates also will take place. That is the limestone, okay, which is actually a flux or the dolomite. Okay, so these fluxes will basically get dissociates and forms CaO and CO2. Okay, and in fact, this is basically the endothermic reaction. The enormous amount of heat is required for this dissociation to take place, and that heat will be supplied from the bottom part of the blast furnace. And this will happen basically around 1000 to 1100 degrees centigrade. And apart from these reactions, there are some other reactions also which takes place at the stack part of the blast furnace. One is the carbon deposition reaction, because since below 1000 degrees centigrade, that is in the upper part of the stack, the CO2, gas is more stable than CO gas. That we can see it from the Ellingham diagram. Okay, at higher temperatures, CO is more stable, and at lower temperatures, the CO2 is more stable. Okay. So, so at low temperatures, CO gas is basically transformed to CO2 gas and carbon. Okay, so this the dissociation of basically CO takes place into CO2 plus C, and this carbon basically whatever it is formed that will get deposited on the iron bearing material. That's why it is called as the carbon deposition reaction. And apart from that, there is a water gas reaction also takes place, especially in the cooler area. Whenever we send the steam steam is basically sent at the clear part of the blast furnace to control the raft. And that is the temperatures prevailing in front of the tuyeres. If it is exceeding beyond the acceptable limit, then to lower down these temperatures, because if the temperatures are very high, then there is a possibility of silicon transfer may take place into the hot metal, and the acceptable range of silicon should be within around 1.4% for steel makers. If it is beyond that, then we have to do external desiliconization. Okay. Anyway, so we have to try to keep the raft temperature within the limits, within the acceptable limits. So for that, we do the to lower down those temperatures, we basically add some coolant, that is steam. Steam is traditionally injected to control the flame temperature, and that steam, when you are injecting, that will basically react with the carbon present in the coke in front of the tuyeres and forms the two reducing gases. One is H2, other one is the CO. Both are good reducing agents. Okay. And this at the tuyer level, this H2O would be almost completely converted to H2. Therefore, the gas mixture in the lower part of the stack typically consisting of CO, CO2, N2, and H2. So, in the stack part, this is the reaction which basically takes place. H2, whatever it is formed, that H2 or whatever it is completely converted in front of the tuyeres and form H2. This H2 gas will travel upwards, and that H2 gas will basically interact with the CO2, because at the lower temperatures, that is the stack part of the blast furnace, CO2 is highly stable. CO2 is basically formed from here. See, so this H2 basically interacts with this CO2 and forms H2O plus CO. This is basically called as a water gas reaction. So these are the some of the reactions which takes place in the stack part of the blast furnace. Then coming to the Bosch region. The Bosch region, if you see, Bosch is basically the region where the Kozub zone basically starts. That is the reason where the root of the Kozub zone basically starts at the Bosch region. Kozub zone is the zone where you have softening and melting of your iron bearing material basically takes place. Okay. So in the blast furnace, you have a Kozub zone where this is the cohesive zone. This is the region which is called cohesive zone. Okay, so here you see this is the start of the cohesive zone. This is the end of the cohesive zone. Like that, everywhere we have. So the start of the cohesive zone actually represents that softening of the iron bearing material, softening temperature, the softening of the iron bearing material. Okay, and the end of the cohesive zone represents a melting of the iron bearing material. Okay, so at this zone only, this is the zone where the iron bearing material softens and it forms a semi-solid, and then it completely transforms into liquid form. Okay, so because of this transformation from solid to liquid, which takes place in the corrosive zone, this zone is having the lowest permeability inside the blast furnace. So if you see, the Bosch is the region where the corrosive zone starts. That is, the roots of the corrosive zone basically start from the Bosch part of the blast furnace. So there in the corrosive zone, we can see that the first slag basically forms, which is of a low melting point. That is a pellet kind of thing. That is FeO2 based slag is formed, and the slag trickles down to the bed of solids, and its temperature rises. As a result, your CaO, whatever it is, dissociate the CaCO3, whatever it is, dissociate into Ca1, CO2, which we have seen that is at the bottommost part of the your stack at around 1000 to 1100 degrees centigrade. So this CaO also start joining into the slag phase. Okay, so it is due to this the slag in the Bosch region attains a very high basicity, and you have hot reducing environments present in the Bosch region, and numerous reactions occurs between the slag, coke ash, carbon in coke, etc. So these influences the final composition of the hot metal and also the smoothness of the blast furnace operation. And carbon present in the coke tends to reduce this SiO2, whatever it is present, and this will form SiO gas. So the SiO2 in the coke ash or slag that will react with solid carbon and forms SiO gas. And this SiO gas is not stable, and it will react with carbon and forms Si plus CO. So in this way, the silicon basically transforms into your hot metal. So also, if you see the decomposition of the silicon suboxide, that will transferring the silicon to the hot metal. This is also possible that 2SiO will dissociate into SiO2 plus Si. So in this way, the silicon also enters into the hot metal, and also as the SiO gas, whatever it is formed here, this gas also may react with the FeO in the slag, where we have discussed that your slag is basically consisting of FeO, SiO2, and CaO kind of a slag is there. Okay, and at the tweer part, once these SiO2 in the coke ash or in the slag, when it get react with the carbon and forms SiO gas, and this SiO gas, whatever it is formed, that starts traveling up, and this gas may come in contact with the carbon which is present in the hot metal,
or it can also come in contact with FeO in the slag. And this is how the dissociation will take place, which forming Fe and SiO2. This SiO2 joins the slag phase, and the SiO, whatever it interacts with the carbon, that will lead to formation of Si and CO, and this Si will join the metal phase. So these chemical reactions suggest that in the Bosch region, a part of SiO2 present in the burden material as well as in the coke ash is likely to get reduced and joins the hot metal. And also the unreactive SiO2, whatever it is there, it joins the slag phase. In a similar manner, you can see the sulfur, whatever it is present in the coke ash, because that is a major source of coke ash. Coke ash is a major source of sulfur. So it is basically present in the form of CAS form or FES form. Sulfur is always present in the combined form, either in form of calcium sulfide or as a ferrous sulfide, and that will basically participate in the slag metal reactions in the Bosch region. And you can see that the CS, the sulfur is present in the coke ash, reacts with this SiO gas again, whatever it is formed here, and that may lead to formation of SiS plus CaO. And this SiS again, as it is a gas at low temperatures, it will reduce and forms Si plus S. So in this way, silicon as well as sulfur both will join into the metal phase. And the sulfur which is present in the coke ash or in the ore also, that will be in FeS, and that will react with SiO and C, and this will form SiS plus CO plus Fe. And this may again lead to formation of this kind of reactions. Fe is a metal, CO is again a gas, it will travel upwards, and SiS is also gas, it will travel upwards, and at low temperatures it will dissociate like this. So in this way, you can see the sulfur and silicon in the hot metal. Besides iron oxide, other oxides also enters into the BF Bosch region, such as your P2O5, MnO, SiO2. So these all basically comes from either iron bearing material or from the fluxes whatever you have added in the blast furnace.